Welcome back. In this video, we're going to talk about exponential growth and decay. And really, exponential growth and decay is the perfect topic to follow on the heels about a conversation regarding logarithmic and exponential equations, because very often exponential growth and decay are modeled using one version of those two types of equations, exponential or logarithmic. And even if it starts as an exponential equation, often we need to use the natural log, or potentially a regular log, but most frequently a natural log, in order to help us solve the equation. So this would also be considered sort of the applied section, where we look at application problems or word problems that involve natural logs and exponential equations. Let's take a look at a few examples. First of all, exponential growth and decay. I've sort of pre-bracketed that third bullet point that you're seeing there that tells us that a growth rate is a percentage that describes how quickly a population is growing. And similarly, a decay rate, and this is where I think you need to maybe underline the fact that a decay rate is a negative percentage. It's not that growth is caused by a number that's larger than 1 and decay is caused by a number between 0 and 1, like some kind of fractional value like 1/2. In this case, we actually use a negative exponent, or rather a negative percentage, in order to describe decay, or when an amount is decreasing, depending on how the amount is decreasing. If it were linear, we would use a line with a negative slope. But in this case, it's going to be more of a curve, and we need to be taking that negative percentage and we will put it into the exponent position. Now in this blue box, we see the basic model. So one way is we have it written in or using function notation. So we see that f of t is equal to a sub 0 times e to the kt. Now f of t tells me that we're working with a function called f. It could be g, it could be p for population. So never mind the fact that it's an f. That's kind of arbitrary. The t tells me that t is our independent variable, and that's going to represent time in the vast majority of cases. A sub 0, that subscript of 0, tells me that it's a starting amount. E is a number, which you should be aware of at this point. It is approximately 2.7, and k is going to be our growth or decay constant. It's going to be the percentage that's either positive or negative that tells us whether we have a population that's growing or decreasing. And t is going to be measuring time. The right-hand equation has f of t replaced with just a capital A, which usually describes the accumulated value. You have probably seen an equation that looks a lot like this, where it says capital A is equal to P times E to the RT. And in fact, we're talking about the exact same thing here. The PERT equation, capital A equals P times E to the RT, is used in financial conversations when you're talking about continuously compounded interest. In this case, when we're talking about exponential growth or decay, we are talking about something that's happening continuously. And whether that's the deterioration of a certain radioactive material that's used to help us carbon date something, that would be a conversation about half-life, which we're not going to do specifically here, but it is seen in those conversations. Or if you're talking about the growth that's continuous of things like bacteria or cancer cells or something like that. Sometimes those conversations are unfortunate and a little morbid. Sometimes they're actually quite positive. For example, if you were growing something in a petri dish, which is going to be used as a remedy, you still have a continuous growth rate. There's no sleeping in those petri dishes. They're always working and growing, as long as there's room enough to grow. And we will talk about that, what happens when we run out of space to grow. So, just so you have something to sort of base this conversation on, it is very similar to conversations that you might have seen about PERT for continuously compounded interest. Now, if our k value, that percentage, is positive, then we're looking at a graph that looks like the one on the left, where we are increasing, so that would be exponential growth, and on the right, with a k value that's less than 0, a negative percentage would be a conversation about decay. So our amount, our a sub 0 amount, or sorry, our capital A, or our f of t value would be decreasing. So exponential growth and exponential decay. These notes you're seeing on these slides these notes were originally created to go along with a particular textbook, but they do apply across the board, not just to Blitzer's college algebra book. Now, in this example, and these applied problems, these word problems that we're looking at, most people don't like word problems, and I don't blame you, because it involves translating the English into something mathematical, and then working something mathematical, and then translating it back into English. So it's triply as challenging as a typical algebra problem. So I can see why nobody gets super excited when it's time to look at word problems. So let's look at this one together. In 2000, the population of the Palestinians in the West Bank, Gaza Strip, and East Jerusalem was approximately 3.2 million. And by 2050, it has been projected that the population will grow to 12 million. And we're being asked to use the exponential growth model, where t measures the number of years after 2000, to find the exponential growth function that models the data. So the first thing we're going to do is use existing data in order to basically design a formula. And then in part B, we're going to use that formula in order to try to make an estimation about when the population will reach 9 million. So the first thing I would do in this problem is to write down sort of the wireframe of the formula that we're creating, which is final amount equals starting amount, a sub 0, times e to the kt. And then I look to the given information. We heard that in the year 2000, which is sort of our starting point, the population was 3.2 million. So that is my starting value, and that's the number that I'm going to use as a sub 0. So I will put in a 3.2 for a sub 0. By 2050, it's projected to grow to 12 million. That's going to be our final amount, 12 million. Now you might be thinking, I thought 9 million was our final amount. We'll get there, just not yet. Multiplied by e to the power of k times, now I know what e is, that's a defined number. I don't know what k is. They didn't tell us our growth rate in this problem, but we did hear how long it's going to take for the population, supposedly, to grow from 3 million to 12 million. That happens over the course of 50 years, from the year 2000 to the year 2050. So that's a total of 50 years, so I'm going to put in a t value of 50. Now I've got an equation that only has one unknown, and this is very typical. You've seen this in problems that involved variation, direct variation, inverse variation, joint variation. Usually those problems are set up where you're given enough information in order to find your constant of variation. And then we'll take that k value and use it to find the answer to part B. But first we have to go through the motions in order to find a solution, not a solution, but in order to find our k value. So our population is growing, so this is going to be a growth rate. We're looking for a percentage, that's our k value. And the first thing we'll do algebraically is divide both sides by 3.2. I'm going to use my scientific calculator. So I'm going to use this TI-30XA single line entry scientific calculator, and I'll articulate what it is that I'm typing into this thing as I go in case you're using the same calculator. For the moment, I'm doing 12 divided by 3.2 equals, and I get 3.75, and I'm going to leave that number on my screen of the calculator. 3.75 equals e to the, and I'm going to write this as 50k instead of k50. Now I need to get that k value down on the ground, as I like to say, and in order to do that, I'm going to take the natural log of both sides of this equation. So we have the natural log of 3.75 is equal to the natural log of e to the 50k. And as I mentioned in the previous video where we were talking about exponential and logarithmic equations, the next thing I'm going to do here is to allow the natural log and the e to basically cancel each other out. Really, the 50k is coming out front and appearing as a coefficient, and then the natural log of e is equal to 1, so it's 50k times 1, which is 50k. Left-hand side of the equation stays the same. Right-hand side becomes 50k. And then we can divide both sides by 50 in order to isolate k. Now, on the left-hand side, you'll notice that I divided the entire thing by 50, not just the 3.75, and that's important. So in our scientific calculator, let's get a k value. I've already got my 3.75 on screen. I'm going to hit the natural log button, which is up in the top row. I touch natural log, I get a number on my screen, 1.32175, blah, blah, blah. Leave that number on my screen, hit the divided by button, type in 50, and hit equals. And I get 0.026435117. I think I'll stop at 35. All right, so that's my k value. Now, if I were working on my graphing calculator, this is a TI-30, or sorry, it's a TI-84, I could have typed in the entire left-hand side of this equation that's on our screen all at once. So I can type in natural log 3.75, and then I'm going to close my parentheses, because when I hit natural log, I was automatically given a parenthesis. So let me close my parenthesis there, and then type divided by 50 equals, and I do get the same number. Now the nice part about the TI-84 is that I can store this value, and I'm going to hit this button down here in the bottom left-hand corner, STO with an arrow next to it, and then I'm going to hit the variable x, which is the normal x that I would use in y equals mode. So let me hit x, so that now it says ANS for answer, and there's a little arrow, and it's pointing at the x, which is going to take this gnarly looking number 0.0264351168, and it's going to store it in my x variable. So if I need to use that exact value again, I don't have to type it in again, I can just use the variable x. So let's set that aside and go back to paper and pencil. Now, I'm going to use this k value, I'm going to plug it back into this equation that I've designed that's sort of at the top of the screen. There we go. Our final amount is equal to our starting amount, which is still 3.2 million. And we're multiplying that by e to the, now I know what my k value is, 0.026435 times t. So you could put a little note right here that says plug back into the equation that we created. Maybe just plug back into formula, however you want to phrase it, but at least you can see immediately on the next line that we're using it. And we're using the initial population. So use the k value and the initial population to move forward with the problem. And what is moving forward with the problem? Well, for starters, what we've already done is found an answer for part A. We used the exponential growth model A equals A sub 0 times e to the kt, in which t is the number of years after 2000, to find the exponential growth function that models the data. At the bottom of the screen, you're seeing the last thing you wrote was the exponential growth function that models the data. Awesome. So if you want, you could put a box around this as the answer to part A. In order to find our answer for part B, we want our population to be 9 million, and we're going to calculate in which year, potentially, according to the model, that we will reach that population. So for part B, let's plug in 9 million for our final answer, or our final amount, equals 3.2, that's our starting population, times e to this terrible k value, times t. And now we have the pleasure of solving for t. No problem. For that matter, in the previous video, if you were with me for that one, we solved equations that looked just like this. The numbers were maybe a little nicer, but otherwise the process is the same. Let's isolate the exponential expression on the right-hand side. In other words, we need to get rid of that 3.2. So we will divide by 3.2. And I encourage you to write a note over here that says, isolate exponential expression. That's the e to the power. All right, so I'm going back into my calculator now. I'm going to use my graphing calculator, and I'm on the home screen. I've still got some other information up there. It's okay, I'm going to leave it there. And I'm going to type 9 divided by 3.2, enter, and I get 2.8125 equals, excuse me, e to the power 0.026435t. And then I need to get that exponent down onto the ground, so I will take the natural log of both sides. Now the natural log and the e on the right-hand side of the equation are going to cancel each other out. I've written that out once in my previous video to this one, once in this video, so I'm going to skip it and I'm going to go directly to 0.026435t. And now we need to divide both sides by that k value. So divide by k. So we have the natural log 2.8125. I'm getting sloppy now. 0.026435 equals t. Nice. Now we're into the calculator. So on my grapher, which is the most recent calculator I was using, I had the 2.8125 already on the screen. I'm going to take the natural log of that value. And you can either hit natural log, which is in the bottom left-hand column. So I'm going to hit natural log, and then if you'll notice, if you're using a grapher, in the bottom right corner above the negative sign it says ANS for answer, and I can recall the previous answer that I had on my screen, but I have to hit the second button first. So I'm going to hit second, and then I'm going to hit ANS for answer, and that puts ANS up on my screen. Right after where I already had natural log. So I'm taking the natural log of 2.8125. I'm going to close my parentheses, hit divided by, and then instead of typing in my k value, I'm just going to put an x in there. So I'm going to recall the fact that I stored my k value in the x variable. It's coming in handy now. So I hit x. So it says natural log answer divided by x. I hit enter. And I get 39.11. And then I'll put a squiggly equal sign indicating that that's an approximate time value. Now let's do what I have heard in a recent study that a lot of students struggle to do, is they struggle to take a final numerical answer and actually relate it back to the context of the question. So 39.11 is a t value. What does t represent? It represents time. Time since when? Time since the beginning of time? Time since the Big Bang? Time since the dinosaurs? What? Go back and refer to the original problem here. It refers to number of years since the year 2000. So this is 39.11 years after 2000, which puts us into the year 2039. What is it that is supposedly happening a little ways into the year 2039? The answer is that this population that we've been examining in this problem is, according to this model, going to reach 9 million people. So what's the answer to the question? Well, this is where it gets a little bit tricky, and it depends on who your teacher or instructor or professor is. It depends on how the question is being presented to you. Is it multiple choice? Is it a fill in the blank? Are there instructions specifically about rounding? Are you allowed to use months? And so on. But what I typically do in a problem like this, and the majority of questions that I see like this, even though we are 39.11 years after 2000, which puts us into the year 2039, let's actually go up and look together at the way this question is phrased. In which year will the Palestinian population be 9 million? Some would say in the year, where did it go? Where's our answer? In the year 2039, the population will reach 9 million. There are other ways that this problem, that the actual question is phrased, that require you to take the 39.11 and round it up. Maybe if the question were phrased, by which year, or by the beginning of which year, will the population be 9 million? Well, in this case, at the beginning of the year 2039, our population was not yet 9 million. We had to go 11% of the way into the calendar year before the population was supposedly going to reach 9 million. But if you have to answer using a whole number, a whole year, then we might even need to take this 39.11 and round it up to 40 and say that at the beginning of the year 2040, the population will have reached 9 million. But at the beginning of 2039, it will not quite be there yet. So be sensitive to the way that the question is phrased. Since this one says, in which year, I think it's safe to say that in 2039, the population will reach 9 million. With 2039 being your final answer. It's a challenging problem right to the very end, right to the point where you have to decide what your answer is, 2039 or 2040, and the fact that you might have to round up even though the decimal is just a 0.11 makes those problems sometimes even trickier. All right, I mentioned we're at the 23-minute mark, so it's a long time ago now. I mentioned that if you were growing something in a petri dish, the whatever you're growing in there could be growing according to one of those exponential growth curves until you start to run out of room. And so that is called a limiting factor, and you can't grow exponentially forever, at least not typically. So a logistic growth model does something where it provides kind of a ceiling. It's a maximum population, or what's sometimes referred to as the carrying capacity. And that's appearing graphically here as a horizontal asymptote toward the top of this graph in kind of a green color. All right. So the blue part of this graph, which is the lower part here, we see that the growth is increasing. It's growing faster and faster. And then it hits this point here where things start to chill out a little bit. The growth is not happening as fast. And in fact, as the growth does continue, the rate of increase in growth starts to taper off a little bit. And in fact, it does plateau just below that horizontal asymptote. So logistic growth models are actually quite realistic. Exponential growth does not last for too long. So the general template, whether you're using function notation f of t or just this capital A value for a final amount or an accumulated amount, the sort of wireframe formula for logistic growth looks like this. And in example 5, we're being given a logistic growth function or model for the world population measured in billions, where x represents the number of years after 1949. And the question is, when will the world population reach 7 billion? So that's a final amount, which means that this number 7 is going to be replacing the left-hand side of this function. And then our task is to solve for x. So basically, we're going to hang out together for the next few minutes, and we're going to do some really fun algebra. But it's good for you to see the example and hear the thought process of working through this. Take whatever bits and pieces are most valuable to you, or if you've already seen some problems like this and you're using it as practice, pause the video at this point, try to solve for x on your own, and write out your work nicely. And then when you think you've got an answer, or if you get stuck, start playing the video and you can compare your work to my work and see if we're doing the same thing. So I'm going to be a little bit lazy here and just kind of scribble in a 7 over the top of this thing so I don't have to rewrite the right-hand side of this equation more times than necessary. And the next thing I'm going to do is multiply both sides of this equation by the denominator. So I have 7 times 1 plus 3.81 times e to the negative, yikes, 0.027x. And the right-hand side of my equation now is only the 11.82. So now this is a good first step because I've gotten my variable, which is in the exponent position, but at least now it's not in a denominator. You might be thinking that the next good step would be to distribute multiplication by 7. But ultimately, I'm trying to get that x value, or you could say an intermediate step is to get my exponential expression isolated on the left-hand side of my equation. So I don't really want to cozy that 7 up to my exponential equation or expression. I'd like to get the 7 away from there. So I'm going to divide both sides of my equation by 7. And if you want to put a little note over here that says that you're dividing both sides by 7, that's a good idea. In my graphing calculator, I'm going to clear my screen since I'm starting with a new problem, and I'm going to take the 11.82, divide it by 7, hit enter, and leave that value on the screen. I got 1.688 approximately. So now I have the 1 plus 3.81 e to the negative exponent is equal to approximately 1.688. Now I'm only writing the 1.688 on my paper, but I'm leaving the exact value on my calculator. And then I'm going to subtract 1 from both sides as I continue isolating the exponential expression. So I've got the 3.81 times e to the power. Subtracted 1 from the right-hand side leaves me with 0.688. On my calculator, I'm hitting -1, enter, which does leave me with the 0.688 on my calculator, making sure it all matches up. Now I'm going to divide both sides by the 3.81, and I will have finally isolated my exponential expression. Divide by 3.81, e to the power. And in my calculator, divided by 3.81, enter, and I get approximately 0.1807. Again, I'm leaving that number on my calculator screen. Whether you're using a scientific or graphing calculator, that number should stick around on your screen as an exact value. Now, in order to get rid of the e on the left-hand side, I'm going to take the natural log of both sides. This is the third time we've done this in this video, I think, so I won't write out all of the steps or talk about it. Let's just have that e go away, and we're left with the exponent. And on the right-hand side, I'm going to write it as the natural log of 0. Well, actually, let's erase that. And on my calculator, I'm going to take the natural log of my previous answer. And remember, you can hit the natural log button and then hit the second button, which on this calculator is near the top left, and then near the bottom right above the negative sign is the ANS answer. So I'm taking the natural log of answer. I hit enter. I get negative 1.71. There are more decimal places after that. I'm leaving them on the screen of the calculator. I'm just not writing them down on my paper. And then I'm going to divide by the coefficient on the left-hand side. So let's divide both sides of our equation by negative 0.027, leaving us just with the x on the left-hand side. In my calculator, I'm hitting divided by negative, which is not a minus sign, it's a negative sign, 0.027, enter, and I get 63.36 approximately. 63.36. Now let's double check, because this is where a lot of us have another sort of challenging point in the process, is interpreting what that number really means. So x, the problem tells us, measures the number of years after 1949. So the question is, when will world population reach 7 billion? So in my calculator, I'm going to type plus 1949. Enter. And I get 2012.36. So let's write a little note here that says 1949 plus 63.36 equals 2012.36. So will it happen in the year 2012 that the world population reaches 7 billion? I would say that this is, and again, this is, it's just a guess, okay? Again, it depends on your teacher, your instructor, your professor, whatever homework utility it is that you're using in typing answers into, whether it's multiple choice, how the question is phrased. When will world population reach 7 billion? I would say, just based on the way that it's phrased, it's very possible that in this case the answer is, right, the year 2012 is not a distinct point in time. 2012 is a whole year. So this problem doesn't say during which year will the population reach 7 billion. It says when will it reach. If I'm going to interpret the number or the year 2012 as the beginning of the year, then our population's not going to reach 7 billion on January 1st of 2012. So I'm tempted to round this one up to the year 2013. So let's actually write that out. Population will reach 7 billion by 1/1/2013. And I'll put a box around 2013 to indicate that that's my final answer. Again, be sensitive to the fact that the answer could be 2012, could be 2013. Make sure you talk to your individual instructor and find out which one they think is most likely going to be the correct answer. For me, I would tell my students, and I'm telling them right now, be careful, read the way that the question is phrased, and I would say more than half of the time the correct answer is going to require you to round up to the next whole year. The art of modeling, and this is definitely an art. There are mathematicians around the globe who are doing modeling, where you take existing data and you plot a bunch of points and you try to see if there's a tendency for the data to be moving in one direction or another. On the left, we're seeing exponential growth. The second graph is exponential decay. The third is logarithmic growth, and the fourth one is logarithmic decay. And those are called scatter plots, where you end up plotting a bunch of points and then seeing if there is a tendency. And there are ways using graphing calculators and other more robust computer software where you can take a truckload of data points and plug them in, and the software will do the analysis for you. Just remember, there was a mathematician or a multitude of mathematicians who had to work with a computer scientist in order to program that software for it to do correct interpretation of your data. So it's nice to know a little bit about what's going on behind the scenes. And our final topic for this video, at least I think it's our final topic, is about expressing equations that are of this format, y equals a times b to the x, in terms of base e. It is, as we have seen, more typical for a growth or decay equation to be written in terms of a base e, which allows us then to use natural log as part of the solution process. So if your initial equation is given to you that's not in terms base e, it might be valuable to make that conversion. In the blue box in the middle of the screen, we see the two equivalent statements, y equals a times b to the x, and then y equals a times e to the power of the natural log of b times x. I'll tell you very briefly, for those of you who might want to know this information, it's not necessary, you don't have to write this down, but give it a look with me. This is equivalent to a times e to the power of the natural log of b all to the power of x. Because when you have a thing to a power, that's the power rule for exponents, you can multiply the exponents together. And if you took x and multiplied it by the natural log of b, it would look like this. Now remember also that e and natural log can be thought to cancel each other out. And so the way that I've written it in red here, if we did allow the e and the natural log to cancel each other out here, the b would fall down onto the ground, the x would come down with it as an exponent, and you would have b to the x. So this would be equivalent to a times b to the x, which of course on the left-hand side of your screen is how all of this started, as y equals a times b to the x. So just a quick illustration of sort of how and why these two printed statements for you are equivalent. All right, so now let's see what this example problem requests of us. We're being asked to rewrite this equation in terms of base e. Oh, great. So all we have to do is sort of match up the pieces and make the conversion. Excuse me. So my a value is the 90. And my b value is the 4.3. And there's the x. And so let's see. Y equals a e natural log b times x. Y equals, my a was a 90, so I'll replace the a with a 90. E to the power of natural log, my b value was a 4.3. Let's put that in. And the x is still just an x. Okay, so I'm pretty sure that this is what my final answer needs to look like. Let's see if that's available as one of the multiple choice options. 4.3, no. Option B leads with a 90 times e to the natural log of 4.3. It doesn't actually sit. Oh. So here I'm seeing the 4.3, but I think that this should say the natural log of 4.3. My only other option is this one, but that doesn't say 4.3, but maybe 1.459 is a decimal approximation of the natural log of 4.3. Let me jump into my scientific calculator, and I'm going to clear my screen a couple times. I'll type in 4.3, then I'll hit the natural log button up in the top row, and sure enough, 1.4586. So if we round it to the third decimal place, we do get the 1.459, and it looks like B is the correct answer. All right, my friends. My hope is that that satisfies your curiosity and demand for some applied problems or word problems pertaining to logarithmic and exponential equations. I wish you the best of luck as you go forward, and please practice some more of those. Make sure that you take anything that was written in bold on these printed notes or that was highlighted, turn those into some flashcards or build them into sort of a comprehensive review packet that you're creating on your own, and maybe include some details of some accompanying example problems so that you've got a really good comprehensive review packet to look at before you go into your next test. And I will see you next time. Thanks.